Oh, we're here, boys. What's going on? We're gonna do a quick post on the twits. Froze Google Chrome. Oh yeah. Fucking love it. Come on, Google Chrome. You can do it. Let's do it. Oh my god. I gotta kill Google Chrome. What is up? Let's get this ball rolling. Alright, I'm gonna just get started. Hopefully my connection's good enough. I'm seeing OBS with some strange signs, but we're gonna keep going. So, last stream we left off, we were here, we had this thing, which... So there's a couple things. This thing, not so great. I mean, as you can see, like, it's really slow. And I left, like I said, I was gonna leave this running, and I was gonna see how it went. Did terrible. It was awful. It did, like, I mean, as you can see, like, it's just like putting stuff off to the side here. No good. It didn't really get much better. And I don't blame it, because it was really bad. And the reason it's bad is because Tetris is not that simple. It's hard to understand like how to play the game. And I mean, we're basically like it's not like I was saying in the last stream. I was talking about how the Snake game in comparison is a very easy game to understand. You just have to avoid the walls. You have to get the food, and that's about it. It's very simple. It gets harder when you have to start avoiding yourself later in the game, which is why the AI had some problems figuring out how to do it later in the game. But just in general, the snake game is a much easier game to understand than Tetris. Tetris is really hard because you have to know how to orient pieces to fit in certain positions, and learning that from scratch, it's not the same as, say, a snake runs into food and now the snake understands, okay, food is good. If a Tetris AI like rotates a piece and it fits in a certain way, like, you can sort of reward it for doing good placement. Like, there's ways to basically like determine whether a placement of a piece was good or not, but that's not universal for every piece. Every piece is different, and there's so many. Not only every piece is different, every orientation is different, and also just the game state in general is very deterministic. You need to understand like what's going on in the game state, or you just need, like, it's really hard to absorb a bunch of different generalized game states to be able to play like that. So this approach is no good. But I have good news. I did a bit of work off stream. I probably should have streamed it, but I didn't. But let me introduce you to this champion. This bad boy with a high score of 253,000 points. That's over 2,500 lines cleared. This beast. This thing is... And this is only generation 7, and it's a beast at Tetris. And what so obviously I've already built it. But what I would like to do, and I actually think it'll be a little more engaging, since I'm not going to be sitting here like coding, typing. I'm gonna actually explain like how this works, how we went from this to this. This is actually the third iteration of the code. I'm gonna explain like how we went from this one, which we did the last stream, to this one, which is the one that you're watching right now, which is a beast. So, I want to let it keep running because it's very good. You know what? Actually, I'm gonna do this. Hold on. We're gonna stick this bad boy right here. Sweet. Yeah, now so now you can watch it. So you can still be entertained. Even if you don't like the code, you can just watch this thing in the corner. Hold on. Let me make that a little bigger. There we go. Yeah, there we go. Sweet. Cool. So I want to just explain the code a little bit. Not going to get too into it because, I mean, generally, I think if you understand the concept that we're using here, you can recreate it your own way. But I mean, I'll explain some concepts, I think. So, first of all, I think what I need to do is I need to pull up the second version, because there's 3 versions. This is the third, but there's the version 2. Okay. So I'll explain the difference between the one we did last stream and the version 2. I'll explain that first. So if I run this one again, you'll see, like, so if you remember how we did this last stream, basically this AI is making keyboard decisions, up, down, left, right. As you can see, like the output of the network is keyboard input, and it's making those decisions every step, every tick of the game. It's making a decision on what to do. So the first thing right out of the gate is that this approach, this one here, the one that you're watching in the corner, does not make decisions every tick. That's the first big difference. What the one that you're watching in the corner does is it makes its decision on what to do at the begin, like as soon as the piece is like comes into play. As soon as a new piece is in play on the board, it decides where it's going to place it immediately, and then just executes that move, which is also why it's another reason why it's super fast, because once it makes the orientation and the left right moves to figure out where to place it, it just drops it straight down to where it's going to be. So the one drawback to it is that it can't do complex moves. So it can't do tucks, where it tucks a piece underneath another piece. Can't do anything like that. It can only make moves where it rotates it and then moves it over a certain spot on the map and then just drops it straight down, which is a slight disadvantage, but it's actually not that much of a disadvantage because you don't really need to do complex moves if you're making the most optimal move every time. I mean, there might be some situations where complex moves would be helpful, but I mean, as you can see, I mean, it's cleared 2,274 lines and it's still going strong. So I wouldn't say it's a real problem for the performance. I think it still does pretty good. But so what I'll explain about the version 2, this is the version 2. So what you can see already is that this still does what I just explained. It makes its decision on where to place the piece as soon as the piece comes into play, and then just executes the move. So these two are very similar. There's one slight difference between the version 2 and the version 3 that you're watching in the corner. The main difference being the use of a neural network. So what I should also explain about the version 2, about this version here that makes decisions as soon as the piece comes into play, is that the way that it chooses what move to make is important. So what I mean by that is like if you calculate every position that you can place a piece in every orientation, in every spot, right? How do you know what move is the best move to make out of those? Now you could come up with like your own algorithm to determine like, okay, like this is how you should place, or like these are the things that you should be looking for. But the real way to do it is to, I guess an easier way to explain it is you score the moves, right? So you would calculate every position that you can place a piece, and you would score each one of those moves independently, and then you basically just choose the highest scoring move. Now, like I was just saying, to do that, you could come up with an algorithm on your own that scores moves based on certain parameters that you find to be the most efficient. Or what you could do is you could employ machine learning. You could basically come up with a set of variables that are important to note, and I'll get into what variables I'm talking about in a second. and then basically you optimize the importance of those variables. That's really what machine learning like is in a nutshell, is or at least yeah, you're basically trying to optimize the importance of input to come up with a good output. And so for this, the parameters that I chose to use are here. So this is the function that finds each move that finds each potential move for a given piece. And what it does is, for each move, it calculates the height of the structure, the amount of lines that would be cleared by doing that move. I'm not sure if anybody's talking in chat. Hold on, let me refresh this page, because I have no idea if anybody's talking in chat. Okay, there's some people. My chat wasn't showing up for some reason. That's weird. All right, we got some people talking. What's up, guys? Git. I'll be doing a Git repository for this soon. I just want to finish it up before I actually put a Git repository. What to get this background? What, for the IDE? I just made a dark theme for it. Okay. So yeah, so this function calculates each potential move for a given piece, or I should say the current piece that's trying to be placed, right? And what it does is, when it places that piece, it figures out the height, the maximum height. So basically, like, what is the highest point that on the game state at that point. It also calculates the amount of lines that would be cleared by placing a piece in a given position. It calculates the terrain height. So the terrain height is different than the current height, in that this is the difference between adjacent columns, or the difference in height between adjacent columns. So I guess if that doesn't really make sense, what that really means is, if you have, right, let's say you have a couple columns here, right? So you have these three pieces placed, right? Or these are technically three columns on the game map. This one has a height of 2, this one has a height of 4, and this one has a height of 3, right? So if you want to calculate the total difference in height here, you would do the absolute value of 4 minus 2, which is just 2. And then you would add the difference between 1 and 3, which is 1. And so that's your difference in height. Your overall difference in height here is 3. And then obviously you would do this for all the columns. And you would calculate the total difference in height of all the columns. So that's what the terrain height does. And then the holes, it calculates how many holes are created, or how many holes are on the map currently. And holes is exactly what it sounds like empty spaces that can't be placed on. So like if one of those big flat pieces covers up 2 empty spaces, those 2 empty spaces are holes. And it calculates all the holes on the total map. And so it calculates these 4 parameters for every move, right? And then what it does is, well, it creates a move list. I'll get into that in a bit. But then what it does here is it scores the move, right? So it passes the parameters into this function that scores the move. What the scoring move does is each Tetris player, so it still uses a genetic algorithm. That part hasn't changed. But instead, what the genetic algorithm is optimizing now is the weights for each one of these parameters. So when a move is scored, the amount of lines cleared is multiplied by a weight that tells how important the amount of lines cleared is to scoring a move. terrain height has its own weight, and holes has its own weight. And so the terrain height and the holes are subtracted from the overall score, because those are basically like the higher terrain height is a worse thing, and more holes is a worse thing. And I'll also get into why this approach is also bad, but I'll get into that when we talk about the version 3 that uses a neural network. So this version 2 approach, by the way, does not use a neural network. There's no neural network involved in this. There's still a genetic algorithm. All the genetic algorithm is doing is optimizing these weights here: the line weight, the terrain weight, and the hole weight. And it's trying to optimize these 3 weights over each generation. But yeah, so then it scores a move. And so we basically create a list of all the possible moves and all the scores for those moves. And then it chooses the maximum scoring move and then executes the move, right? And so what happens is the genetic algorithm each member of the population just plays a game with those specified weights. Those weights aren't changed while it's playing the game. It just plays a whole game with those weights, and then the genetic algorithm does the mutation and the mutating of the weights to try to get better performance, and that's it. So that's the big difference between this version and this version, is that the version that we did on the last stream, the neural network is making a decision every tick of the game on what to do, and it's making that decision in keyboard input, whereas this version doesn't use a neural network, and this version simply takes these 3 parameters and tries to figure out how important they are to making a good scoring move, and it scores every possible move and then just executes the highest scoring move. And so that's the main difference. I can get into a little bit more about how, coding wise, how each move is calculated, although it's a little more in-depth and might be hard to explain. Also probably because I didn't do it in the most optimal way. I just did it in a way that made sense to me. But I can get into that if need be. But what I would like to get into is the difference between the version 2 and the version 3. So, not that. So that is gone. So now the difference between this version, right, and this version, right, we can put that one away. So I think the first thing that you can notice is this version uses a neural network, and it actually uses a neural network to do the scoring of each move. So the reason that this approach is better than this approach is simply because of the simplicity of this approach. So in this version, Felix, in the third version here, the neural network is used to do the scoring. But in this version, there's no neural network at all. In this version, we simply have just 3 weights that are assigned to those different parameters, and those weights are optimized. I mean, when I say weights, that doesn't necessarily mean that there's a neural network being used, because a neural network implies, a neural network kind of implies the formation of a layer, really to be some sort of a neural network. This approach is actually closer to a regression problem, right? I mean, a regression problem is simply AX, MX plus B, right? It's just you've probably, you might have not known it, but you've done regression problems in like not really regression, but you've done like what a regression line is in like math class for years. Like mx plus b is just the function that determines a line. What regression does though is regression tries to find the x that fits the line as to best fit, right? So this approach is closer actually to a regression problem, because if you think of each one of those parameters, the terrain height, the line weight, and the hole weight, if you think of those as x, and or they'd be three different x's, and you think of each one of the parameters as your m's, like three different m's, you just have three different mx's, right? And you're trying to optimize the x to give you the best performance, I guess. Yeah, so the reason that the neural network actually performs better is this essentially does the same thing. If you, for example, like if you essentially, like if these were your four inputs right here, imagine that this layer here does not exist, right? But imagine that these were your four inputs and they were directly connected to the score with weights, right? That's essentially what this version is doing. The only difference of using a neural network is you introduce this layer here, this bridge between the inputs and the score. There's this layer in the middle here, and this allows for the formation of a bunch more connections, a bunch more weights. And the advantage to that is that you can model more complex behaviors, and that's simply because instead of like I was saying, this problem is more of a linear regression problem, where you have just like m1 times x1 plus m2 times x2 plus m3 times x3 equals your y, right? Which is a linear regression line. The neural network is a nonlinear regression, and I mean, I can get into a little more about like why neural networks are nonlinear regression models, if people want to, but it could get a little complicated, and I'm probably not the best person to explain it. But the introduction of these layers, or a layer, at least one layer, like this is just all that defines a neural network, is just having this extra layer in there, is that that allows for the modeling of much more complex behaviors, right? And so if we think about it like let's take an example. If we were using this approach, right, where we just have these three parameters and we multiply them by some specific weights, right? And we've predetermined the function here. The function is lines cleared times lines weight minus terrain height times terrain weight minus holes times holes weight, right? So we've predetermined the function here. It's this minus this minus this. So if the model like determines that lines are very important, terrain height is not important, and holes are somewhat important, right? Well, what happens if the terrain height gets really large? Like there might be something wrong with scoring a move without taking into account terrain height, right? Or say terrain height weight is very big, so terrain height is prioritized over other things, right? With this predetermined function, it leads to simple behavior. Can still work really well. In fact, like this doesn't do terribly. This can actually do very well. But the reason that this version works much better is because you can model more complex behaviors, right? The introduction of the layer, and this is like the entire reason that neural networks are good at doing stuff like this, is because they can model complex behaviors. They can model more than just like a simple regression line. They can actually like there could be I guess a connection that like once terrain height reaches a certain point, it becomes very important to influencing the score. But until it reaches a certain height, it's not very important, you know. So like you can get some behaviors like that, and that's the reason that they're so powerful. So yeah. I hope that I didn't lose everybody there. It'd be easier to explain if I could like think it out ahead of time. I'm kind of just shooting stuff off the top of my head though. More complex, such as stacking one side of the game board until a light blue piece. Yeah, exactly. So I've even observed this. I also observed that sort of behavior when I introduced Tetris. So, I mean, I had to do a bit of research into how Tetris is played, because it's actually, the scoring for Tetris is kind of complex. But essentially, I didn't get too into it. I just modeled simply like in Tetris, if you clear 4 lines in a row, that's known as a Tetris, and you get a bonus score for clearing 4 lines as opposed to just like 1 or 2 or 3. Every line cleared is 100 points. So if you clear 3 lines, that's 300 points. But if you clear 4 lines, that's 800 points, right? So you get a bonus on top of that. So that's why you can see here that this model has scored 2 Tetrises. So its score is high. Like if it was just 100 points for every line cleared, this should be like 318,000, but it's 328,000 as opposed to 328,000, right? Because it's gotten 2 Tetrises, so it's gotten a bonus score. And using this score as opposed to just simply the lines cleared, this model, by the way, only uses the lines cleared as its fitness function, right? The advantage to using this score as opposed to the lines cleared is it can allow it to understand the importance of getting Tetrises to getting a higher score. And so I've actually observed that behavior in this model as opposed to this model, where this model actually, maybe not this specific version, but I've seen versions that actually do that, where they'll stack one side and leave one column open and place lawn blue pieces down one side to get as many lines cleared in one go as possible. Obviously it's not perfect, because if there's any holes, because the model can't do really complex moves, the absence of being able to do complex moves actually does hinder the ability to get Tetrises consistently. It is actually much harder to get Tetrises if you can't do those complex moves where you tuck pieces in to fill those holes, because any holes created are going to just mess up the Tetris. But I have actually, like, this model has actually learned how to do that sort of strategy. So those sort of behaviors are really only possible through the use of, like, using a neural network to model those complex behaviors, as opposed to just this, which is closer to a linear regression problem. Yeah. So I kind of don't know where to go from there. I can get more into the code if people want to get into the code. Maybe some people might want to see. So I can also get that out of there. Maybe some people want to know like how certain things were done, and I can explain the code. But yeah, this works pretty well. Much better than I thought it would. But so there are some things that I don't like about it. And there's some things that I like a lot more about it. One thing that I don't really like about it is that it doesn't make decisions in real time. They're all predetermined decisions, and then it executes those decisions. I guess it's not really that I don't like that. It's just that it doesn't feel like what I like about the real-time decision making is that it's closer to like a person. Like it's closer to like a human actually playing the game, versus this isn't so much like a human playing the game, unless the human had super reaction time and could make split-second decisions, which a lot of pros actually kind of do, but they still give like thought input over time. It's like no human is just instantly makes a decision and executes on that decision. So I don't necessarily like that about this approach, although I understand its advantage, especially from like just like an execution standpoint. So with this setup, basically as soon as a piece comes into play, right? As soon as a piece is placed in a new, we have our new piece that we're trying to place, right? It calculates every possible position that it can place that piece in every orientation and every position along the map. It calculates every possible position, right? And what all the neural network is doing is taking those parameters that I talked about, the current height of the structure, of the whole structure, the terrain height, which is like the difference in terrain for each adjacent column, the amount of holes created by placing a piece in a certain position, and then the amount of lines that would be cleared by placing that piece. It takes all those parameters, passes it through the neural network, and then the neural network just simply spits out a score, just some value, and that score is recorded for each possible move, right? And then what it does is it just takes the highest scoring move. So all the neural network is doing is optimizing how to score a move. That's really all that's going on here. Is this neural network is figuring out how to score moves to optimize the play. So how different is the code to introduce the mechanic of calculating the position of pieces if they were slipped under the prior existing stacks? So the difficulty with complex moves, I guess it honestly wouldn't be too difficult to introduce. We might actually be able to try to figure out how to introduce complex moves. The difficulty with them is the way that each move is calculated, right? Is so it'll start it in its origin position, which is up at the top here, right? And it'll move it over one space, rotate it, and then just place it down. And that'll be one position. Then it'll maybe move it over to the same position, but rotate it twice instead of once, and then place it. And then rotate it 3 times and place it. And so it calculates every rotational position for all these spaces. But it does that at the top, and then it just places it straight down. So in order to program in complex moves, we'd have to place it all the way down, and then we would also have to see if we can place it side to side. And not only once it's all the way down, but at every time we move it down, we would have to see if we can place it side to side. Which wouldn't be impossible. It just it might add a little more complexity, but I could actually try to see if we can do that. Which computer program? This is so this uses this is written in processing, which is a visual IDE, which allows you to make visual programs like this. That's why I use it for building these game programs, I guess. It just makes it's easy to make visuals in this IDE. Yeah, I mean, that might not be too complicated to introduce. We could actually try that. Just determining, really the hard part would be figuring out if it actually worked or not, because you'd actually have to observe a complex move. But we can try that, yeah. Okay. So, I guess in order to do that, I'll explain a little bit about how this this code works, because this is the actual code. I'm gonna turn this music down just a tad. Because this is the code that actually determines each move, and then does the scoring and then returns the actual move. Yeah, so essentially the way this works is we have an array list of moves and move scores, and this is simply just because we can't it would just be too complicated to store the moves and the move scores in the same array, so I just put them in two different arrays. But these arrays will have the same size, and each index will be like corresponding to the index in the other array. Which other games? So I mean, if you check out my channel, I've done Doodle Jump, and I've done Snake, Java Snake. I've done like, and those AIs were both written in this this IDE. Yeah. So we have a couple loops here. Yeah, no overflow stacks here. So we have a couple loops here. So this first loop just runs from 5 to -5, and this is going to represent the x position. So moving over every x position, right? And this inner loop is going to represent the rotations, right? So we start at 0, we go up to 3 rotations. And yeah, so the first thing that we do is we copy the current tetromino. We don't want to override the current tetromino because this is just a test, so we just create this testing tetromino. And then this loop simply just rotates that tetromino however many times, whatever value of j we're on. So initially it's not going to rotate it at all. Then when j is 1, it's going to rotate it 1 time. When j is 2, it's going to rotate it 2 times. When j is 3, it's going to rotate it 3 times. That's just how this works. So that just handles the rotation. And then this just makes sure that there's not going to be a collision, right? So this is just to make sure that like we don't like when we're moving from like to a side, that there's no collision there. And so we just take so if you remember, like the tet position or the tetromino position is the x, or the 0th index is the x direction, the 1 is the y. So it just checks to see if the x position plus this I, right? This I represents our x, our new x coordinate, right? So if the current x position plus the new x that we want to add on, if there's no collision there, then what we do is we just increase the y until we get a collision with the bottom. So this just adds on to the y position until we reach some collision, meaning that we've either hit a tetromino or we hit the bottom of the screen. Then we create a copy of the tetromino position. This is also so that we don't override the current tetromino position. We just want to make a test. And then we just add that I to the x and then add our new y value. Excuse me. We add our new y value to the y direction. And then we create a testing map, which is just a copy of the game map, and we insert that tetromino in that new position, right? And then once we've done that, then we calculate all our variables here. And then we create a integer array called moves list. This is basically just an array that's going to have the values of the move. So if you remember, the way that we do moves is we input a direction, and that direction is a numerical value, either 0, 1, 2, or 3, and that numerical value represents what move to make. 0 is rotation, 1 is the down key, which just updates the game step to skip. 2 is to move to the left, and 3 is to move to the right. So we create this move array, right? Just an array of integers, and it has the size of the I plus the j, and the reason for this is if I is 5, then we're gonna have at least 5 moves where we move to the say the left, right? And then j is the amount of rotation, so we need at least that many rotations. And then I just found I had to add 1 here. I think it's just because we needed an extra move to the right. It just worked. I didn't really think too much about why we had to add an extra move to the left or from side to side, but it just wasn't necessary. It was just a big problem if we didn't. And so then all we do here is we just add this many moves for rotation. So this is the rotation. I also found that doing rotation first and then moving is important, rather than moving to the side and then rotating. So we program in all the moves for the rotations, which the amount of rotations that we want to do is just j. If you remember, like j is the amount of times that we rotate the tetromino. So we just program that many moves of rotation. Remember, rotation is a 0 move. When we eventually execute the move, it'll be a 0. And then we add the rest as just like left or right directions. So this just is to make sure that if I is less than 0, then we want to move to the left, because we want to move in the negative direction. If I is positive, then we want to move to the right, which is 3. So we just program in those moves, and then we add that move list to our array of moves, or array list of moves, that is, right? And then we score the move. We pass in those parameters that we calculated here. We score the move, and then we add that to the move scores. So we do that for all the moves. This calculates all those moves and fills up our moves array and our move scores, right? And then here this just calculates the highest scoring move, and returns the highest scoring move. If the moves array is empty, it just returns 1, which is just a down. So it's not going to affect anything. This is just in case there's no move calculated. A new move list item would need to be made to include a different game step rate to choose a move, slip right or slip step. So in terms of the complex moves, I guess what we would need to do is we probably have to do it in here, right? So we'd have to start off by making the move list initially here, actually. So I'm gonna see if this will work. So right, so let's make our moves list up here, right? And then here we can just do right, so this is just going to add those rotations into our move list, right? So complex moves are also tough because a complex move could be a rotation, and it can also be like an X or Y move. So it can be any extra move. But basically, like, we'd have to add the moves as we do them, instead of down here where we just, the way we were doing it before, where we just we add all the moves at the end after we actually make the move. We'd have to add them as we actually perform the moves. So let's see. I'm going to just leave this one running over here, and we're going to actually open up that window capture again. So just let it run. Forgot to do that. Let's see. Okay. I'm also gonna clean up my naming. I don't usually name scheme my loops, which is not really great practice. Yeah, so we'll just name that X add instead, and then this is, I'll name this one rotation. Don't need this anymore. Yeah. Lack of commentating? What do you mean? Oh, lack of comments. Yeah, I usually add comments after. That's usually the last thing that I do. That's mostly just because, like, I understand in my head how it's working. But when I put it out there, that's when I decide to comment. I have some leftover comments from other. Sometimes I'll comment like during the code. Or during when I'm doing it, just to give myself visual references. But in terms of like how things are working, I understand just like from doing it myself. But yeah, when I post this, I will have it commented. Don't worry. So let's see. Hmm. This might be a little tricky. Okay. So let's do that here. That's not necessary anymore. So I think here's what we're gonna have to do. So, no, whoops. I wanted to put this. Okay, so here's an example where I'll put a comment. I'll put the and so what I'll also have to do is oh, I see. This is gonna have to be an array list. Okay. It's fine. Oh, sorry. This will also probably be better to have it as an array list. That way I don't have to like keep track of like the size. But what this does mean is that I'm gonna have to have an array list of array lists. Yeah. Now it's getting complicated. Not really, but it's just funny. So this is gonna return an array list of integers, which means this moves to make. It's gonna be an array list of integers, and then this has to be a get function. And that's good. I love how many people I lost or that just stopped watching once we started getting into the code. When I was showing off the fancy Tetris, there were like 15 people in here. Now there's like 6 people. It's just interesting. Hopefully the little Tetris in the corner is somewhat entertaining. More entertaining than my code, I guess. It's kind of fun to watch. I enjoy just watching it. I mean, it's only on generation 8, and I've had it running for probably 3 hours. But I mean, it is running in like kind of a slow speed. I can actually increase the speed of that like drastically. I'm gonna play Tetris at hyper speed, which will be fun. This is, what language is this? This is closer to Java. It's not Java, but it's Java syntax. But the actual language is processing. So, okay. So. Now we have to have 1. Well, I mean, I wouldn't really consider processing its own language, quote unquote, but like, it's not, I mean, it's Java syntax, or at least the default version of, like, you can get it with different syntactical styles. You can actually like download like processing Python, which is like all the syntax will be like Pythonic, but I find like the Java is the easiest one to do, and it's the default, but it's not really its own language. It's just, I guess it's the syntax, or it's like the whole style of like, it doesn't use like main functions. It uses these like JavaScript style, like setup, draw, setting functions, like these kind of things. It's like a fusion between Java and JavaScript. But if you know Java, you'll pick it up like nothing. It's so easy to understand if you know Java. It's actually like, this is actually the one, I don't really code in Java anymore, but this is like the thing that keeps me remembering how to code in Java, because it's like the only thing that I still use that is Java oriented, which is cool. Anyway, so let's see. So we'll have to do it here. So we'll do another check for game collision here, but we'll do See, this is difficult because we're gonna have to repeat moves. Because say there's a position where we could either move the piece to the left or move the piece to the right for a complex move. If we do it one way, then we have to repeat the same move until we get to that point, so that we can test both directions, which would be kind of annoying. Anyway, let's just keep trying this. So +1. Then I guess we can just try it this way for now. Yeah, so like we're gonna have to find a way to replay the same move up until the complex move. So like let me just like show what I'm saying. This is really bad. Ignore my shitty paint. But like, say we're trying to place like a piece like this, right? Like one of these like T pieces, right? Just imagine that these are all, I don't know, bear with me. But like, see here, we can move this piece here in like, if it's going down like this, right? We can move it like in here as like a complex move, right? But then we could also like, so we also have to figure out how to repeat the same move pattern until we get to this point so that we can like test this move here, because we want to test both of them. We want to test every move, right? So if we have two possible complex moves, we have to be able to test both of them. But like, how do we determine? See, that's tough, because like, how do you, like, if you do repeat the same like step, you have to be able to ignore this move if you've already done it, which is hard. That's hard. It's not impossible. You just have to figure that out. Am I using CPU or GPU? Well, processing doesn't really use GPU because it's not really it's not like a library for machine learning. It's all written from scratch, and the neural networks aren't really that complicated. But when I do machine learning in Python, which is like mostly what I work in, I'm always using GPU TensorFlow. You kind of have to if you're not using your GPU for machine learning or deep learning specifically. Then you're just wasting resources. CPU training is really, really slow. Especially if you're using, like, especially if your network has any kind of complexity to it, you have to be using your GPU. Like ConvNets, you cannot train a convolutional neural network on a CPU. It will not work. It'll take fucking months to do something that a GPU could do in like a couple hours. Although, so if you're not using your GPU, you should definitely figure out how to install GPU TensorFlow or PyTorch or whatever you're using. Are you using Neat? No, this isn't Neat. This is just a simple feed-forward network. It still uses an evolutionary strategy to update the network, but it's not Neat. Neat implies like augmenting topology. So like a Neat algorithm actually like not only uses evolution to update the network weights, but also the architecture of the network. I honestly find Neat kind of redundant and not really necessary, because it's like it can be useful in some situations, because like a simpler network might be more optimal in some situations, but technically like a feed-forward network can learn the same things that a neat network could. It just might be a little harder for it to figure out those parameters, but like Neat, the advantage of Neat is really that like the architecture is simpler. Or the architecture can be simpler. That doesn't mean that it is simpler, because the like your Neat algorithm could optimize to build a really complex network if it figures it out, or it could just keep it simple. So like yeah, I don't really mess around with Neat though. I don't really find it too useful. Yeah, exactly. Feed forward networks can model all the things that a Neat network could and more. Neat networks just have the advantage that simplicity can be an advantage in some situations, but I find that it's not really that necessary. Yeah, it's cool. Neat is a cool thing that it exists. It's just like not really practical, and it's not really used outside of like this kind of a scope. Like if you're actually like building neural networks for like real applications, nobody uses Neat. And that's mainly just because like using like evolutionary strategies to update neural networks is a terrible idea. Like practically, it works for stuff like this because this stuff is so simple. Like these programs are like, these AIs are like really really simple. Like this neural network is tiny. This is like, if you're actually building like neural networks for real applications, your neural networks are huge, and evolutionary strategies are just not going to cut it. You need to use backpropagation to actually do that. So that's like that completely defeats the purpose of anything like Neat. What if your function recursively elected the most valuable move for each simple move? That's possible. Really, it's just like a matter of it'd have to, yeah. You could use recursion for some. Actually, this could be used recursively. It might get a little complicated though. I kind of am a little. Recursion scares me sometimes because like recursion can get really out of hand if you don't understand exactly what's gonna happen. See, the thing is, it has to calculate we have to calculate all the moves and score them before we can choose the best scoring move. We can't, like, having made a move, we don't know if it's the best move because we have to test all other moves first. So that's yeah. Interesting. Let's see. So here this introduces some complex move strategy. So basically, like, this while loop tries to move the piece down and adds like a down move, like every time it can move the piece down. But then every time it moves it down, we're running one of these checks to see if we can either move it to the left or the right. But what I mean is, like, once we add this move, like say we do this move, right? Then this whole thing's gonna reset, and it's not gonna reset to the, like, it's not gonna execute the same move so that we can test this move here. It's gonna be a whole different position. Here, I'm gonna go heat up my coffee. I'll be right back. Policy network? Well, policy networks don't really apply to something like this. Policy networks are like a reinforcement learning approach, which I have actually been working on at Tetris AI using reinforcement learning. It's proving a little difficult though, so I haven't really shown anything much about a lot of stuff about it. But yeah, I mean, I guess in a way you can think of like this network as like technically a policy network, because it's learning it's learning a policy for what is a good move and what isn't a good move, I guess. But there's nothing like, there's no real distinct feature to like a policy network. Policy just like a policy network just implies that the network is understanding what move will maximize reward. In this case, like what move is going to maximize the score for the player. That's what it's trying to figure out. Anyway, what are we gonna do here? This thing's still going strong. Hasn't beat its high score yet. This one's getting a lot more Tetrises, though. This one's gotten 30 Tetrises. I might have to build more loops. So I think what we're gonna have to do here is we're gonna have to add some extra loops to test each possible move. So here, so like we'll have to have I just want to make sure my naming scheme is right. No, this is actually this is good. I mean, it gives us something to do on stream, because I didn't really have much else planned besides just like showing what I had done and explaining it, which didn't take as long as I anticipated. Oh, watch this! It's gonna get a Tetris. Boom, Tetris. Nice. Pure machine. Boom. Satisfying to watch. But see, it's cool. Like watching this thing play. Like you can even see. I lost. Damn. But like watching it play, you can see that like when the structure gets too tall, it starts to prioritize clearing lines faster. Like near the bottom, it actually like tries to set itself up. It isn't always trying to clear lines. It's actually trying to set itself up for Tetrises, is what I'm assuming it's trying to set itself up for. But then when it gets to the top and it starts to struggle, it actually starts to prioritize clearing lines because it needs to save itself. So it's actually like really cool to see that behavior. And that's the kind of behavior that the other version that didn't use the network to score moves, that version wouldn't be able to model that kind of behavior because the height of the structure like wouldn't really be recognized as much importance, or like it couldn't like understand that like once the structure gets really high, it has to start clearing lines. It doesn't like that's not really something that it could have learned. Or like how to set up for Tetrises is not really something that like that kind of a function could have learned. That's only something that like a nonlinear function can learn. Yeah, complex moves are like tucking pieces. Like if you have an L piece and you tuck it into like a corner, or like you said, like rotating T blocks and stuff like that. Like those that's what we're trying to do right now. We're trying to find a way to program complex moves. It's pretty difficult though. I'm not gonna lie. Is there a way to do an R and N so it can tell itself about holes? I mean, you could you could use any kind of network architecture for something like this, I guess. Whether it would actually be practical to use an RNN for a problem like this, I can't really say. It depends like what you mean by like tell it about holes. I guess I just don't really understand what you mean by that. because it can, like, it counts the amount of holes that are on this, like, that are on the structure currently. Like, every time it places a piece, it calculates the amount of holes that are created. So I guess I just don't really see the purpose of an RNN for understanding holes. But maybe you have a better idea of what you were trying to say. Well, it's not really that it can't find gaps in the structure. It knows it knows how many gaps are in the structure. It's more just the problem that I'm running into right now is trying to figure out how to code in how to make a move, but then, like, so the way that it's set up right now is like this outer loop controls how many, like what position in the X direction we're testing, and then this loop tests out controls what rotation position we're testing. The complexity really comes in like once those move sets are added to our move list, right? Then we start to just move the piece down, right? Like that's what happens here is the piece just gets moved down. But what we want to do is we want to be able to like move it down and then test if we can either like move it like to the side, like to either side. But the problem is that once we do that, we want to test the same move that we got up until that point and then move it to like the other side. But the way that this is set up right now, we can't really do that. So I'm trying to think of like a possible redesign of like how this is set up, because this was like this is I mean, at least like from what I can understand, this is like the easiest way to do this kind of move set calculation, but there might be an easier way. I wonder. I wonder. So like. Since we have it set up to do these like in this move list sort of way, it might be possible to like take like a brute force approach and just brute force every combination of move sets. That might work. Yeah, we're trying to see, like, because we're trying to be able to do complex moves, because, like, right now I can't do complex moves. So we're trying to figure out a way to code in the complex moves, because it's not as simple as just, it's not as simple as it sounds. That's why most people usually avoid complex moves or at least, like, I've seen, like, one Tetris AI before, and like they didn't use complex moves because it's kind of difficult. But I wonder if we could take like a brute force approach. Because the way that our move list is set up right now is just basically just an array, right? And that array is made up of just some numerical values, right? So like 0 is a rotation. So like let's say this is our move list, right? And then this is just all ones, right? So what this means is that this is rotate once, move to the, I think that's the left, move to the left twice, and then just move down. That's what this move set means. And what this whole function is doing here is trying to create that move set. But it might just be possible to brute force it, like brute force every like possible combination of move sets. And then just test the ones that work, or just like execute them, and then only the ones that work count as valid moves. Although that could also get really complicated really fast too. Well, I mean, brute force, I mean, I'm using that term like, not really like what I mean by brute force, but, like this, like technically, this is kind of like a brute force approach already. But what I mean is not really brute forcing like every possible move, but brute forcing how to create that move set. This is a tough one. Oh, AlphaGo. Yeah, AlphaGo is really cool. Well, so they didn't actually predict all possible outcomes, because that's actually impossible. Because there's more possible outcomes in a game of Go than there are stars in the universe. So it's actually impossible to calculate every possible move or every possible outcome in Go. So what AlphaGo actually did is they use a Monte Carlo tree search, but they optimize the tree search using a neural network. That's actually like what the reinforcement learning approach was the reinforcement learning was to optimize the tree search. It was actually a really interesting approach to reinforcement learning, because Monte Carlo tree searches are actually like very efficient for doing for that kind of a problem, where you have to expand basically a giant tree and like look at all the possible outcomes of a tree. like I was saying, like you can't look at all the possible outcomes of Go, but what you can do is you can basically figure out what outcomes you want to look at, like, because you don't need to look at everything. You only want to look at the outcomes that like have significance, and that's where Monte Carlo comes into play. Like it allows you to only look at moves that are beneficial in some way, or I guess like it depends on like what your tree is trying to look for. But in like their case, like you only want to look at the like a select number of of really good moves, and so that's what it allowed him to do. But the reinforcement learning part of it actually was to optimize the tree search, which was pretty cool. But yeah, AlphaGo's insane. That was what's also even cooler. Well, maybe not cooler, but if you haven't seen Alpha Star is it's like AlphaGo on steroids. I mean, they're two different things, because like AlphaGo was the game of Go, and Alpha Star is freaking StarCraft 2, which is like insane. So you should, if you haven't seen Alpha Star before, you should look up Alpha Star and watch that, because it's crazy. They trained a reinforcement learning algorithm to play StarCraft 2, and it's beat like a couple grandmasters. And StarCraft is a hard game. StarCraft is very, very hard, but from like it's like a different kind of difficult. Like you can't really compare it to like AlphaGo or like anything else, because AlphaGo comes with its own set of challenges. Like AlphaGo's challenge is that like there's so many possible outcomes, or there's so many possibilities given a single move. But like StarCraft has the complexity that like the game itself, like you have to think of so many things. You have to take so many things into account, and not only that, but you have to think about like how you like using your troops in a specific way will affect the game in the future, things like that. So it's like a completely different set of challenges, and it's incredible in its own respect. Oh yeah, and they also trained it. Yeah, they did. They limited it so they could only, I think they like said an average pro StarCraft player makes about like 800 actions per minute or something like that, and they limited their AI to only make that amount of actions per minute because they wanted it to be like at a human level. Like they wanted it to be better than people, but they wanted it to be able to like for example, like this Tetris bot right now is running at like reasonably human level, right? But like I can crank this thing up to play like, let me just make sure that I didn't fuck anything up. Oh. Technical difficulties, hold on. I was trying to make a point here. But like I could crank this thing up to play at super speed, right? I might have also fucked it up in all the editing that I was doing. But like I could make this play at like super speed if I wanted to. just want to... I did something wrong. What did I do? I messed something up. I mean, I moved a lot of stuff around here, so I just gotta get it back to working. I should have saved it separately before I started editing it. I'll figure it. Hold on. It's like one. This is like the problem I was having before. And I fixed it like some janky way. Yeah, I changed that, but that shouldn't be a problem. I mean, let me comment that out and just see. Yeah, see, that's still kind of busted. Yeah, it's not. I'm gonna just. This is not ideal, but this is what we're doing. I didn't really change anything, so reverting it back is not going to hurt anything. still busted. Hang on. What is still busted? Something is still busted. Something's still busted. I'm stuck in an infinite loop. Well, now I'm not. No. Okay. No, I'm having an out of bounds exception. Oh, right. No, now I'm still stuck in an infinite loop. Yay. Where's my loop? Where's my infinite loop? I don't like infinite loops. Where is it? It's here. I know it's here. But yeah, I know it's there. It's just like, I don't know. It's incrementing. It shouldn't. Well, I'm just gonna look at the version 2. because this one worked. It's the same code. Oh, it's the same thing. I'm doing the same thing. Am I not doing the same thing? I think I'm doing the same thing. What possessed me to write in Java? Just because that's what processing is. I don't usually work in Java though, so. What am I doing different? Let me just put this back exactly how it was. It is y at equals 0 before the while loop. Oh, I'm definitely blind. Plus y add plus 1. Y add plus plus, yeah. I'm definitely missing just one thing. Oh, wait. No, it isn't there. I know it's in there. It just... I wonder if it's because of something else. Shouldn't be. Yeah, well, I replaced xadd. I replaced the I here with xadd, so that's still correct. These are plus xadd. It's this loop. I don't understand why this loop is busted. It doesn't make sense. It's the same. Check collision shouldn't be busted. I didn't touch that. That's really busted. Hold on. I have no idea how to use the debug feature here. I just thought I'd might be helpful. How do you use this thing? I have no idea. Don't really care. I'm just curious. I'm gonna restart that. Yeah, so it's not just processing. Thought it just might be processing being stupid. I'm gonna just here. I'm gonna make this easy. I'm gonna just copy all of this and just put it back. No? Okay, so it's not that then. It's something else that's causing that problem. How? I didn't change anything else. What the hell? That really not working. What the hell, man? What the hell? That's so weird. That's weird, man. That's strange. For some reason, there's an infinite loop in this. What the hell is happening? How did I break it that badly? I don't understand. What? No. I don't understand. Oh my God. What the hell is happening? This doesn't make a drop of sense. It's the same freaking thing, dude. What the fuck? I'm so confused. Oh, you've got to be kidding me. Please tell me that's not it. It's absolutely it. Are you I have shit brain. I have such a shit brain. I had it at 0 FPS. Oh, you hate to see it happen, man. You really fucking hate to see it happen. I'm so fucking dumb. Oh, I have garbage brain, man. Garbage brain. Garbage brain. Such garbage brain. Such garbage brain. Fuck. Fuck me, man. Alright, we're doing this. Oh, man. That's so annoying. That just wasted so much of my fucking time. Over that. Over that stupid problem. Oh my god, that's so annoying. That's so fucking infuriating. All that time just wasted. I guess this is just gonna turn into me cleaning up code. Whatever. That's what happens when you just don't look at other code. You get tunnel vision. I'm gonna fuck shit up so bad. See, part of me thinks that I had it set up for, like, in a way, for a reason. But I don't listen to myself. I shouldn't have to do this, I don't think. That shouldn't be the problem. No. What did I do? That shouldn't mess with anything though. It's so weird. Hold on. So the first thing I should do is just get it working the way it was, but like with an array list. I didn't make the third version this stream. I made it off stream. But I've been editing this version on stream, yeah. I know what I did. I'm just trying to convert it over to use an array list instead of an integer list. Or an integer array, I mean. Okay, so that's working. And my question... My question is, why can't I put this out here? I guess, hold on, let me just move it piece by, like, slowly. I'm gonna convert it slowly. Not gonna rush myself. That fucked it up royally. Okay. So, can't do that. Why not? I don't get why I can't do that. Why doesn't that work? What the hell? What is actually happening? Oh. Fuck. Okay, that's working fine. But I don't understand. This should work. This should work fine. I mean, unless I'm just like... Okay, no, that does work fine. I'm just looking at, like, the first one is just, like, really shitty. I have to wait till a couple die to actually see one that's doing well. Okay, yeah, that works fine. So then I should be able to move this stuff out there too. I guess at this point I'm just trying to clean up this code. I don't really know if I'm gonna be able to do the complex thing, like complex moves right now. I'm gonna have to think about that. Okay, no, I think this is working now. No, it doesn't have to be created in this if statement, because if this if statement gets skipped over, then the loop, this outer loop recreates, which recreates the new list. So the list isn't persistent. It's persistent into the scope of this, but like when this loop iterates again, this list will be recreated. So it'll be a new list. Now, this is working fine. I just had to wait a couple because like it looked like it was really shitty, but that was just because like that was like the first generation, and that was like a shitty generation, I guess. It's actually working fine. So, alright, so next thing I want to try is moving this out. There's no real purpose to doing it this way. I just like, I don't know, like part of me thinks it's cleaner to do it this way. That should work. Yep. Okay. I don't know, like that just looks cleaner to me. The code, at least. So if you'll notice, I also have this species thing. That just like indexes each player in the population. So there's 200 players per population, and this is just their ID. Yeah, it was on Gen 8 before we killed it. So this is only the first generation. Actually, it's technically generation 0, but Okay, this is working fine. I'm actually going to change the gen thing to start on gen 1. Not that it really matters. Just like makes more sense, I guess. It's kind of bugging me. What? Hold on. What happens if I remove that? Why is that? Am I blind? I don't know. That looks... So it rotates first, then checks for side collisions, then moves the piece down until the collision with the floor, then scores it. So it rotates first before anything. That's weird. I'm not even gonna bother with it. I was just like messing around with the visualization for this because like this line does not look straight. How do you rotate your pieces? So, okay, where's the rotate function? Is that in here? No. It's in here. Yeah, rotate tetromino. So, this is just how to like rotate a matrix. but like in a like not a square matrix. That's the important thing. You don't want to just rotate a square matrix. You're trying to rotate an oddly shaped matrix. So you're wait, hold on. So you're saying check for possibility of a specific move. If yes, move on. If no, add move to the list. Check for specific move. 3, 2, 1. See, it's yeah, like I mean that's like the flow, but like in terms of like how to do that effectively, that's the part that I was trying to think of. But I think it might just be easier to like calculate every like brute force position. Well, that's like a dumb way of saying it, but like you basically just like calculate every, like if your move set is like a vector of numbers, right? You can just calculate every possible vector of those combination of numbers. Like if our numbers are like a combination of 0, 1, 2, 3, you just create a vector that has every combination of those things, and then you just test every move. I mean, that's like a really bad way to do it, because that might be like really resource intensive, so I might not do it that way. I just have to figure that out. But in terms of rotating the matrix, this is the rotate code. So you just get the n by m dimensions of the matrix. You create your output, which is the inverse of that, right? So instead of n by n, it's m by n, right? Because this is like, if you have a 2 by 3 matrix, now you want to make a 3 by 2 matrix since you're rotating it. And then you just go through element wise and just like set the inverse elements. In terms of like this is like you want to like cross over, so you do like n minus 1 minus I. Like it's easier if you draw it out. Like looking at it in code, it doesn't really make sense, but if you like draw it out, it makes way more sense. But like if you want to like take a look at that, that's how I did it. This thing is gonna go. So we're gonna set it on. We're gonna set it off to the side. Yeah, exactly. That's what I mean. Like you can just brute force every permutation of that vector. That's a really inefficient way to do it, but like it could work. Yeah, that's the downside. Is it would be very computationally intensive and very slow. So finding like an efficient way to do it would be more beneficial. That's just the challenge right now. See, but the reason that I wanted to put the move list out here and start it before we get here is because now what we can do, right, is while we're in here, we can make a new loop here, right? And I just, Yeah, that's so. I'm trying to keep these making somewhat sense. But like now that we're in here, right? We can make a basically just move it, do array list. Hold on. I want to look at how to copy and array list. Can you wait? So they have a clone? No. Yeah, no, I mean, like, so, but what I'm trying to do here is like, I want to preserve this move set before we start doing complex moves, because there might be multiple complex moves all on this first move set. So I want to store this move set first, and then make a complex move set that uses this one initially, and then explore every complex move set within this move set before moving to the next simple move set, I guess, is like I hope that doesn't, I mean, that probably makes no sense, but that's what I'm trying to do here. So now I'm making a complex move set. So just copy all of those elements over. So now this move list complex is a copy of this one. And now we can start exploring the complex moves while in here. How long have I been coding on this? We did a stream last week, or a couple days ago. Probably like 3 or 4 days, off and on. Not like straight, but like it's probably been a 3 or 4 day project so far. Okay, so this loop is basically going to try to tuck it in a corner. Don't need that, so this will be game map collision plus LR. Yeah, so basically like this sets up the moveset with the rotations initially and the X position at the top. So this is like at the top of the screen before it actually starts moving down, right? So it sets up like every possible rotation and every possible X lateral position at the top of the screen. Then this starts dropping it down. This while loop here starts to drop it down, and every time I drop it down I start testing new lateral positions. So that's where you start getting this complex move. You create this complex move copy, so it's going to test both lateral positions at every step down. Yeah, so like this for loop moves from 1 to -1. This just makes sure that it doesn't run at if it's 0, because then we just get stuck in an infinite loop. We only want to be at 1 and -1, moving left to right. Yeah, that's why I put it in the bottom. That's why I put it in the corner, because I thought it'd be interesting to look at. I'll actually make it bigger, because it's not taking up a lot of my screen. It's pretty cool to look at. It's running at hyper speed. I'm actually gonna turn off flux. I just realized my flux is on. Oh my god, my screen's so bright. Oh, the screen is so bright. I don't know if that actually changed the stream or anything. Probably not. If that didn't change the stream at all, let me know, because I'll turn it back on for myself, because it'll spare my eyes from the blue light. How did you make it so the bar doesn't show up on the little window. What bar? Oh, because it's just an OBS window capture. It's not actually there. Like, I can drag it into the screen. It's off screen right now. This is just that in the corner. It's just an OBS window capture. Is only for you. The screen looks the same to us. Okay, I'm gonna turn that shit back on. It's hurting my eyes. Okay, thanks. Because the light blue one could overhang by 3. What time is it in your place? Where I live, it's 4 o'clock in the morning. Dude, go to sleep. It's only 11 here. I'm in the US, so. Dude, you should catch some sleep. Jeez. Although I'll probably be up until 4 in the morning, to be fair. Okay. Alright, so. So I can also so I can take this shit, right? Catch my drift. And I can shove it in here. Ooh. Yeah, hold on, so. Yeah, I don't think OBS picks up the flux, but I just couldn't tell because all my screens are tinted red. I just wanted to make sure it wasn't like that. Okay, I'm gonna stop my guy short here. Sorry. I'm gonna run this. I want to see if it'll actually make a complex move. Oh, wait, hold on. I forgot one thing. So, I want to add the complex here. Oh, it looks like it did. Yeah, it's making complex moves. See it move that piece over mid-game? Or mid-thing, I guess. We'll see if it actually, like, works out at all. Oh, you know what I'm also gonna do? I should include the size of... Because, like, I don't want it to... Hold on. When choosing the best move, so... If move scores dot get I is equal to move scores dot get max index, if move scores dot get less than moves dot get max index dot size. Basically, I'm adding a condition so that it'll choose the score with the lowest size, or a move set with the lowest size. Because, like, if you notice that it was like going left then going back right and placing, I want to make sure that it doesn't do that, and basically, like, choose the move with the shortest. Like, if two moves have an equal score, or two move lists, I guess two move sets, whatever you want to call it, like, have an equal score, just choose the one that's the smallest move size. That should fix that issue, so it shouldn't choose. It should only make the shortest move. This might just make it perform really badly. We'll see. I'll have to test it out, I guess. Why is it still doing that, though? It's still going left to right. Oh, wait, hold on. I might have found a fatal flaw. Yeah, so can't do that, because that'll condition it so that it, like, the only moves that it's going to make are ones where it moves left to right, which is bad. Take this out, so I can't have the while loop. So the only problem with this, oh, you know what? I can just do that. Great, more infinite loops. Oh, now it's running really slow though. Huh. Hmm. See, the problem is we just exponentially increase the amount of moves that we have to make, that we have to decide on. Because we basically just added another 10 moves laterally. So not only do we have to calculate 10 positions at the top, so there's 10, there's 10 rows or columns, and each one of those 10 positions can have 3 rotations. So there's 30 possible moves for each piece, like at maximum. There's 30 possible moves. But now we just added another, so not only that, but then every vertical position, we added another 10 moves. So we just added like a shit ton more moves to calculate. That's my only issue here. I mean, it can do the moves though. Like, it's doing moves. Like, look, it just tucked that piece. Look at that piece. It just tucked it. Oh, you know what? Oh, wait. We might be able to actually get away with this without this. Oh, this might be the spawn. What if... Hear me out. Oh. Hold on. What if we take this out? Make this XAdd, because it's kind of redundant to have 2 lateral moves. Like, because out here we're just calculating the lateral moves at the top, but we can already just do that in here. You feel me? Like, we don't need to do it outside. It just doesn't really make a difference. We can just calculate the lateral moves on the way, like on the way down. And if that's the case, we actually might be able to do that with the rotational moves too. That'll save a lot of computation. And you know, if that's the case, could even just do, we could do both of them. We could just take that entire thing and stick it in here. This might burn up in smoke and not work, but we're gonna try it anyway. So for each Y position, we basically instead of doing the lateral and rotational stuff at the top, we're just, for every Y position, we're doing our lateral testing. This does mean that we have to do this outside. So this has to be here. Hold on. This could end up in utter failure. Hold on. I just want to gather my thoughts here. I don't think this will work. No, that's not going to work because this doesn't allow for the ability to move to the side, move down, and then move over again. This doesn't allow for that. This just moves down, moves side to side. So it's just the inverse of what we were doing before. We need to have bidirectional control. Yeah, that's not going to work. Oh, don't let that be the farthest back I can go, please. Jesus. Come on. Oh, I have to figure out how to put this back together. Oh, I wanted to see it make that tuck, man. Oh, you know what? We're gonna have to... You're gonna have to make a duplicate of that. Yeah, this is just gonna be like exponentially slower, and I'm honestly not sure if it's gonna be like any better. How is it getting held up like that? It shouldn't be able to get held up like that. Why is it calling that so many times? It should only call that once. Oh. Because it's for 200. That's why. I forgot that not only is it calculating that for one Tetris, but it's calculating it for two. It's calculating all these moves for 200 of them. No wonder it's taking so long. I'm honestly wondering if it's like, I mean, this can work, but it might just be too resource intensive. It might not be. I don't know. Because we just made it like exponentially longer to calculate each move, because there's 10 more moves for every level, so that's another 200 possible moves. So it's not now it's not 30 moves per Tetris, it's like 250 moves per Tetris. Because it can move 10 this way, 30, so 3 different rotations, 10 each direction. Right? So that's 30 moves just at the top. So before it was only calculating a maximum of 30 moves per Tetris. But now it not only does that for each Tetris, but then every level it moves down, it checks laterally. So that's another 10 for every down. So at max for every vertical position. So there's 20 vertical positions times 10. That's another 200 vertical positions. So it's now it went from 30 moves to 200 moves. That's a lot. That's a lot. I see a lot of moves. So I mean, it might just be too resource intensive to actually bother. What's up, Shry? Yeah, I mean, and I'm honestly not sure like how, like, the using complex moves might actually be too complicated. I mean, it shouldn't be too complicated to score. It's just like a matter of, I don't know. But you notice how, like, as it gets higher up, it starts to do it more because, like, it has less moves to calculate when it gets towards the top because there's less vertical positions. So you see now it's really speeding up because there's less vertical positions to calculate. Yeah, it might be worth a revisit. I'm just not sure if it's necessary, honestly. I mean, I'm probably also, like, I would probably also fuck something up. So, it might not even be working correctly. Here's what I'm gonna do. I'm gonna copy this code. I'm gonna name it version 4. I'm gonna name that version 4. And I'm gonna revert this back. Just because I want to have the original version. And I'll probably see if I can iron out the bugs. So I think I had it like this, if I remember. Hold on. Test. I think that's the original way it was set up. Oh, I also should, wait a second. I might have messed something up. Hold on. I'm just gonna get this version back to where it was, and then I'm gonna open up the other version because I think I fucked something up. This I actually don't need. On. Something's broken. I broke it. Where did I break? What did break? Nope, something else broke. What else broke? Why did it break? No, that shouldn't be affecting it. What is the problem? I'm a little confused now. Oh, back to fixing this shit. What did I break? Yeah, I mean, I'm gonna keep fine-tuning that. I just want to get this back to fucking working, but I don't remember. I don't see what's wrong with it. Although I'm probably blind. What is the problem? I don't think it's that. Oh my god, what is happening? Why isn't it working? Alright, hold on. I want to... Because I want to look at the version 4 that I just saved, because I think I messed something up here. I just want to do that while it's fresh in my mind. This here. I didn't do this part correctly. Forgot to do that. So hold on, let me. Maybe this can help me figure out what the fuck I did wrong here. Yeah, it just takes so long to actually calculate the moves. It's unbelievable. Okay. That's so bizarre. That fixed it. Why does that work now? That's so strange. Before it had to be equal to. What the fuck happened? Oh, wait. I think I know why. Because this... Well, I don't know. I actually no fucking clue why. It has something to do with the fact that I'm using an array list, I think. Instead of an array. Fuck me. I don't know. Doesn't make sense. God, this feels like a Mark Rober video now. Guys, we're in a Mark Rober video or whatever. I'm about to like spill some science knowledge on you right now. Well, I got it back working. So, yeah, I'm gonna I'm gonna keep working on the complex moves thing. That's going to take a little bit of thinking. I don't even know if it's possible because it might be just so computationally intensive that I might not be able to do it. But yeah, I think I'm going to end it there. We've gone almost 4 hours. Wow. Jesus, time flies. You'll be forever a Gen 0 fan. Respect. Love Gen 0. It's even like, I mean, it's good even at Gen 1. Like it's kind of insane how good it is even at the first generation. But I mean, I guess it goes to show that like it just like it's pretty simple to learn, but it's like the later generations really is just mastering. Yeah, but I think I'm gonna end it there. Thanks for sticking it out, guys. I know it was a long one, but I appreciate you guys sticking it out. I'm just gonna do the shameless plug. I'm not it's not like not trying to push it, but if you guys feel like you might be interested in supporting me on Patreon, there's a link in the description. Every donation is heavily appreciated, and it's worth, in my opinion, the $3 that you would spend on an Americano at Starbucks. That's just me talking though. But yeah, thanks anyway for everybody who came by, hung out. Really cool. I want to keep doing more of these streams because they're pretty fun. It's fun to think aloud with an audience. Bounce ideas off you guys in chat. Yeah. So anyway, I'm gonna probably put together some sort of a video for this pretty soon. But until then, I'll probably do another stream in a couple days. But yeah, thanks guys for hanging out, and I'll catch you guys later. All right, bye.